In the previous video, we went over a rather technical mathematical derivation of the continuity equation, and this derivation involved, in a rather essential way, manipulations with various operators. The appearance of operators is actually not specific to the particular problem of continuity equation, but they appear actually throughout quantum mechanics and play a very important role generally in the mathematical formalism of quantum physics. In this short video, I would like to make a few general comments about operators and relate them to quantum observable quantities. So in order for me to trace the origin of the operator objects in quantum theory, let us go back a little bit and remind ourselves the way the Schrödinger equation was derived. So I use derived here in quotes because there is no really rigorous way to derive the Schrödinger equation as a fundamental equation of quantum theory, but we sort of follow the logic that the early practitioners such as Schrödinger used. And the first piece of information which was essential was the experimental fact that quantum electrons and other quantum particles may exhibit wave-like properties. And in order to explain this, we sort of introduce in an ad hoc fashion a plane wave function which would explain the data essentially. And in this wave function we also introduced the momentum and the energy of the electron, which according to another piece of information that is known from the theory must be related to one another using this dispersion relation. It's basically kinetic energy of a free particle, mv squared over 2 or p squared over 2m. Now the equation itself was constructed in order to ensure that the plane wave function would come out as its solution and this dispersion relation would be respected. And so this is what equation actually looked like, and it involved the second derivative with respect to the coordinate and the first derivative with respect to time. Now the next step, and this is really the first time we sort of thought of introducing an operator, was to write the equation in a different way. So we had the sort of universal left-hand side, which is just I h bar, the derivative with respect to time, and the right-hand side was a sort of energy operator, the Hamiltonian, where we associated with the momentum that would have appeared in the classical theory this guy, which is minus I h bar gradient, which indeed is an operator that converts, that acts on the wave function. And the last step in deriving, again in quotes, the Schrödinger equation was to generalize this energy operator, called Hamiltonian, from being the free energy operator, which is just p squared over 2m, to kinetic energy plus potential energy. And this is the fundamental Schrödinger equation, which remarkably describes all of non-relativistic quantum physics, including this describes atomic spectra and even many particle systems, theory of metals, theory of superconductivity. Everything is contained in a compact way in this remarkable equation. And it's sort of also remarkable that you can get to it from very few simple experimental facts by adding small pieces together and getting to this fundamental result. Now, but in doing so, we were forced indeed to introduce, at least three operators. So the first one we have seen already many times. It is the momentum operator minus I h bar gradient. And by the way, I should mention that the minus sign is really sort of a convention, which is sort of must be consistent with the convention we choose to describe a plane wave in a sense. It could have been plus, but this is the convention that we use. So apart from that, we also introduced the potential energy, which enters this h hat. And in this setup, the potential energy naturally appears as just multiplication operator. So we can think about a coordinate operator, multiplication operator that, there should be actually a vector here. Multiplication operator that simply multiplies the wave function. And finally, the kinetic energy itself, sort of the first step was appeared here, and it was the second derivative with respect to spatial coordinates. Now, it turns out that the appearance of operators was not unique just to this sort of derivation of the Schrödinger equation, but sort of they pop up throughout quantum theory whenever we deal with any analogs of classical properties. For example, when dealing with the angular momentum that in classical theory is R cross P, so all we have to do to make it into an operator is to put a hat actually on top of the corresponding quantity. So P here would be replaced with minus I h bar gradient according to this, and R will be just multiplication operator, etc. So we can always find a proper generalization of classical properties. So that's great. We established that operators do appear in the mathematical formalism of quantum theory, and from the mathematical point of view it may be quite interesting. But what physical significance do these operators really have? Unlike their classical counterparts, which can be measured directly in a classical experiment, let's say we can measure momentum, angular momentum, position, the operators cannot be measured per se, they are operators. So how do we associate an experimental observable with them? So in order to answer this question, we're going to use a sort of method that oftentimes is used in science by first answering the question in a simple special case and then generalizing the results to a more general category of objects. So, and the special case that we're going to consider is the measurement of a coordinate of a quantum particle. So the Born rule tells us that the absolute value of the wave function squared gives us the probability distribution function of different positions of a quantum particle. Now, in general, if we have a probability distribution function, let's say capital F of x of some random variable x, so if we want to find, let's say, the mean value, the expectation value of this x, what we're going to do is we're going to average x, integrate x over all possible values weighted with this probability distribution. So in full analogy with this, we can define the mean value of a three-dimensional coordinate by integrating the wave function, absolute value of wave function squared, with the coordinate over the volume, over the basically all three-dimensional space. There is a square here. So, and this is a natural definition of the mean position. So we can rewrite this definition as so, because psi, absolute value of psi squared, of course, is simply psi star times psi of r. So now comes this generalization of this definition of the expectation value of a coordinate to a general case of an arbitrary quantum mechanical operator. So let's say we have a classical property x, let's say momentum, angular momentum, coordinate, energy, whatever. And let's assume we know the quantum mechanical operator associated with it, some x hat. So the expectation value of this quantum observable x is going to be calculated in full analogy with this equation by simply replacing the coordinate operator in this equation with the operator x, whatever it is. So for example, if x happens to be, so let's say if x happens to be momentum, then we're going to simply write it, the expectation value of momentum is going to be an integral of v star minus I h bar gradient of psi, etc. So it turns out that this conjecture actually works in that it is consistent with the experimental data. And the experimental data implies that if we, let's say we have an ensemble of quantum systems, each described by wave function psi of r, and if we measure this quantum, some property x of these quantum systems, we're going to get different results. But the average value of this measurement is going to be consistent with this definition of the expectation value. And so it becomes a very important and basic principle of quantum mechanics that I reiterate here, namely that, first of all, physical observables are associated with what I didn't discuss, self-adjoint operators acting on the wave function with the expectation value defined as above.